Second law states any spontaneous event, chemical reaction, the entropy of the universe is going to increase. Something a little more qualitative that we can just look at things and describe might be a molecular interpretation of entropy. Like a gas is less ordered than a liquid, which is less ordered than a solid. Any process that increases the number of gas molecules is going to lead to an increase in entropy. And we'll come back and look at some phases here in a second. So now you get the third law of thermodynamics, which states that if you have a pure crystal, it can't be a diamond with a nice color because the colors are due to impurities, and you can get it to 0 degrees Kelvin, we say it has an entropy of 0. And we make that statement. That's a reminder that entropy is a state function. Here's our definition of what is 0 for a piece of matter. It's a pure crystal, meaning solid and ordered like a crystal, and has no thermal energy. So as you heat something up beyond 0 degrees Kelvin, bonds vibrate. The bonds on water vibrates enough, the solid will melt, turn into a liquid, start moving around more, will turn into a gas. So Ludwig-Boltzmann came up with the Boltzmann constant. And here's what I mentioned the other day, where we looked at Q divided by T for a system that's at equilibrium. And I said it's something we can measure in the lab. It has the units of joules per Kelvin. Entropy always has this unit, joules per Kelvin. And he came up with this idea that each thermodynamic state has a specific number of microstates associated with it. And entropy is equal to the Boltzmann constant times the natural log of microstates. So the other day we had that flask with the 2 gas molecules, and with 2 of them we had a 25% probability, and we had 4 microstates. I guess the word I was looking for was thermodynamics. I like to think of entropy, probability, and statistics. So here is our pure crystal. It's at 0 degrees Kelvin. You see everything is nicely ordered, and we say entropy equals 0. We increase the temperature. It's still a solid, but things are kind of vibrating around like they do when they're not at 0 degrees Kelvin. And so now we have an entropy above 0. It might be kind of hard to measure, but we can measure an entropy between 2 states due to it being a state function. So in general, entropy will increase when liquids or solutions are formed from solids or liquids. Gases are formed from solids or liquids. And as we saw earlier, the number of gas molecules increases. So here is an interesting plot. Can anybody tell me how this differs from a heating curve?
It's not measuring time.
Yeah, the heating curve has temperature on the y-axis and maybe heat or time on the x-axis. Some interesting things to note. So you have a solid, it's a pure crystal, it's at 0 degrees Kelvin, has 0 entropy. As you heat it up, molecules start to vibrate around. They're still locked in position, so you still have a solid, but entropy is increasing. And then the big jump for a phase change. This is what sticks out to me. In a heating curve, our phase changes were flat as far as temperature goes. Here they're vertical. It's a big jump in absolute entropy. And then similar thing, we're heating the liquid, the molecules have more motion, thermal motion. Finally, their kinetic energy overcomes the intermolecular force, holding it in a liquid state, turns into a gas, and then we see a big change in absolute entropy here. And then as the gas temperature increases, so does the entropy. We can look in at the appendix, and there are some entropies tabulated for various chemical species, and we can use this equation to find a standard change in entropy. Just like we calculated a standard change in entropy for a reaction using standard enthalpies of formation. Everything's almost exactly the same. Products minus reactants is exactly the same. Summing things up is exactly the same. And the N and M are the coefficients in the balanced chemical equation. Everything's the same there. So I kind of like this slide, and I kind of don't, because sometimes it makes a liar out of me. But most of the time, the liquids have higher entropies than some solids. Compounds have higher entropies than elements, and there might be some weird exceptions.
Water.
Gaseous water. So here is Mr. Gibbs, and he was interested in maybe work, and he came up with this thing called Gibbs free energy, and that might be energy available to maybe do some work. Reactions with a large negative delta H values tend to be spontaneous, like combustion reactions, right? Once you get a forest fire started, it pretty much goes on without outside intervention. The outside intervention to stop it is firefighters. And so a negative sign, what word do we use to describe that? Endo or exo? Right, exothermic. And that might be somewhat intuitive because we imagine reactants at a higher energy level than products. And we all know water likes to flow uphill. No, it flows downhill. We see a theme where things try and reach low energy states. So here is a reaction enthalpy minus temperature times the change in entropy. And we put these together and we call this Gibbs free energy. And the sign of G predicts whether a reaction is spontaneous or not. So some of you might have seen me on the whiteboard draw a rock up on a hill and then a cabin down below, and I talk about potential energy, kinetic energy, and the ability to do work. So here's reactants, here's products. This looks like a exothermic reaction. Reactants, if you get them going, they can go to products and give off some heat. Well, we can maybe harness that and do some work. Now here's something we haven't considered. This low energy well where it says equilibrium mixture. Our next chapter is going to be on equilibrium. And so here is an interesting slide. This is the formation of ammonia from the elements, and we can approach equilibrium from either side. What does that mean? Over here, we just have nitrogen and hydrogen, and they'll react and start forming ammonia until we reach this magical position here where this system is at equilibrium. We have some reactants and we have some products. Now this system where they use to make this, there's catalyst, there's a bunch of heat, it's at a high temperature. If you were to just put pure ammonia in there, the reaction's going to move this way and it's going to create some nitrogen gas and it's going to create some hydrogen gas. And then it reaches a nice magical spot where you have some nitrogen, you have some hydrogen, and you have your ammonia product. So here's pure ammonia. We'll spontaneously go this way. Here's our pure reactants. And here's a situation where nature has the perfect balance between the two. That's going to be a good ending spot.